So complex ions. Transition metal ions are often good Lewis acids. So remember that Lewis acids are electron acceptors, right? Water molecules can act as Lewis bases because they have lone pairs on the oxygen. So the water molecules can hydrate transition metal ions. So silver ions are actually hydrated in solution. You'll have two water molecules donating their lone pairs to the silver ion, and this will form a complex ion. You don't actually have silver ions bare by themselves floating around. So this is a complex ion. A complex ion contains a central metal ion with one or more ligands attached to it. So in the green salt that we made, it was iron and oxalate, right? Iron was the central metal atom, and oxalate ions were the ligands that are bound to it. The ligand can be a neutral molecule, or it can be an ion that acts as a Lewis base. If we add a stronger Lewis base, it will displace the water in the complex ion. So here's our complex ion with silver, and we add ammonia. Ammonia is a stronger Lewis base, and so it will displace the weaker Lewis base, and we'll get a complex ion of silver with ammonia, and the water got displaced. For simplicity, as we often do with acids, we often leave the water out of the equation. And so we look at silver aqueous, which we understand would be hydrated, plus ammonia will form this complex ion. And this is an equilibrium, and the equilibrium constant is called a formation constant. So again, it's the concentration of products divided by the concentration of reactants. Yes?
So why wouldn't it form NH4 and it's just NH3?
Well, NH3 aqueous is actually an equilibrium between ammonium hydroxide and ammonia, but there is ammonia present. And it's the ammonia that will complex the silver, because ammonium is not a Lewis base, because the hydrogen is sitting on that lone pair, so it doesn't work anymore. So here's another table of lots of numbers. These are formation constants for selected complex ions in water at 25 degrees Celsius. You might need to look at this later. So let's look at an example. You mix a 125 milliliter sample of a solution that is 0.0117 molar in nickel chloride with a 175 milliliter sample of a solution that is 0.25 molar in ammonia. After the solution reaches equilibrium, what concentration of nickel remains? And the formation constant for the nickel ion, complex ion, is 2 times 10 to the 8th. So this is a lot like that question on the exam that you all hated. Yeah. So we've got nickel ion, and we've got ammonia. And they are going to form a complex ion. And you're not expected to know what the complex ion is. We tell you right here. So it's nickel with 6 ammonia molecules surrounding it. And that's still going to have a charge of 2+. So then in this chemical equation, there's 6 ammonias that come for every nickel. So we're starting out with 125 milliliters of 0.0117 molar nickel chloride. So 125 times 0.0117 is 1.46 millimoles of nickel. So we've got 1.46 millimoles of this, and we've got 175 milliliters of the ammonia, which is 0.250 molar. So 175 times 0.25 is 43.75. That seems really big, but I think that's just what it is. Now, if we try to do an ice table here, X is going to be so close to the nickel that it's not going to work. And so what we need to do, because this formation constant is so large, is we need to react it completely and then see how the equilibrium comes back. So if I have 1.46 millimoles of this, and I need 6 millimoles of ammonia for each, I've got plenty of ammonia, right? So all of the nickel is going to get used up. And how much of the ammonia am I going to use? I'm going to use 1.46 times 6. So 8.76. So 34.99 millimoles of that are going to get left. How many millimoles of the complex ion did I make? 1.46. So the nickel is the limiting reactant. All of the nickel is going to react. I can calculate how much of the ammonia is going to react with it, 6 times as many millimoles. I can figure out how much ammonia is left over. 1.46 millimoles of nickel is going to get me 1.46 millimoles of the complex ion. This is like the before, the Ba tables for the titrations. We've got an amount, we add some stuff, and then we see how it reacts, right? So these are millimoles, but I need concentrations. So what's my total volume now? 125 plus 175. 300 milliliters. So if I divide this by 300 milliliters, 0.1166 molar. And then this one divided by 300 milliliters. 0.00487 molar. So the equilibrium constant is very large. The products are highly favored, right? So I'm going to push the reaction to completion all the way to the products, and the equilibrium is going to come back a little bit. And that's what I want to calculate. I want to calculate the little bit that comes back. So coming back, this will be minus x, and this will be plus x. That's 0 molar. What's the change for the ammonia? So I'm going to take some of this and recreate these guys. So if I lose one of these, how many of these do I make? 6. So this is going to be plus 6x. So I end up at equilibrium with x 0.1166 plus 6x, and 0.00487 minus x. So my equilibrium constant is 2.0 times 10 to the 8th. That equals my product, 0.00487 minus x, divided by x and 0.1166 plus 6x. And what's the power on that? To the 6th. Yikes, right? This is a situation where x is going to be small. So x is small means I can ignore those minus and plus x's. So x is going to be equal to 0.00487 divided by 0.1166 to the 6th power times 2 times 10 to the 8th. So that's the concentration of nickel that remains. Not very much. Any questions? I can tell you guys don't like this. Complex ions are going to have an effect on solubility. So the solubility of an ionic compound that has a metal cation that will form complex ions, that solubility will increase in the presence of Lewis bases that will complex that ion. So we just talked about how silver and ammonia form a complex ion. So here, if we put silver chloride in ammonia, as the silver chloride dissolves just a little tiny bit, the ammonia complexes the silver ions. It's removing the product, and so the equilibrium shifts and dissolves more. The most common Lewis bases to increase solubility are ammonia, cyanide, and hydroxide. Ammonia used to be a very common household cleaning solution. It smells really bad, but it's actually really good at cleaning stuff because ammonia complexes all kinds of stuff, makes them more soluble, and you can wash them away or smear them around. Yes. Looking at silver chloride, adding ammonia will change the equilibrium constant by a factor of 17 million. That's big. So we can figure that out by looking at the equation for silver chloride dissolving. And here we've got the solubility product constant. And then we can look at the formation reaction for forming this complex ion. Silver ion plus ammonia, making the complex ion with its formation constant. When we add two chemical equations, we multiply the equilibrium constants. So if I add these two equations, the silver ion, this water isn't reacting. It's one of the complexed waters, is losing a hydrogen ion to the water molecule in the solution. And so now we've got 5 water molecules in hydroxide. If we add base to this, we are neutralizing the hydronium ion that's formed here, and this will happen more, right? And so it can do that with another water to end up with H2O4 and 2 OH minuses. And again, adding more hydroxide will cause that to go even further to AlH2O3, OH3, and this is insoluble. This is aluminum hydroxide. It's equivalent. But if we keep adding base, now we begin to form complex ions that are soluble again. So at low pH, we get the formation of this complex ion with aluminum, and so we get solubility. pH neutral, we end up with aluminum hydroxide, which is not soluble. At high pH, we form complex ions again, and it dissolves. So aluminum is really the only one that you need to remember, but chromium 3, zinc, lead 2, and tin 2 can also do that.